So we want to look at this strategy, which we call a stationary policy. So let me backtrack just a little bit and remind you of some notation and some notions. So, where is my pen? So, V star was our value function, right? So, if the initial state is x, V star of x was defined to be the best discounted present value that I can achieve starting with initial state x, yeah, if I'm free to choose over all possible strategies, pure or randomized, that are available, right? So all possible feasible strategies. And we showed that this value function V star satisfies Bellman's equation, this equation here, right? And we were saying, look, yeah, everything is nice in this optimization problem. In fact, everything is nice and finite and bounded. And so this max is going to exist for every initial state x. And suppose I consider a strategy, call it sigma star, that depends only on, only on the current state x. So for instance, at any time t, suppose the state is x, so not necessarily at time t equals 0, but I look at this problem starting at any time t, and the initial state at that time t is x, right? And I consider a strategy sigma star, which simply tells me that if the current state is x, you choose a certain action A. So sigma star is a mapping from the set of states to the set of feasible actions, right? Where the action sigma star of x is the maximizer of this right-hand side. Okay, so corresponding to the relationship between values, this is the maximizer, it's the argmax, right? So what is special about this strategy sigma star? The first thing is that it is stationary, so which is written as the second thing here, which is it doesn't depend on histories other than the current state, right? And secondly, simply by looking at what is being maximized here, it satisfies a one deviation property. That is, you cannot improve upon your payoff by deviating just here, wherever you are at time t with current state x, okay? It's maximizing the present reward plus discounted by beta expected reward tomorrow, because from tomorrow onwards, you're valuing each state at the maximum discounted present value that you can get, right? If you wish, I can put a y here, right? And so the question arises, is sigma star optimal in the sense that playing this strategy or this stationary policy sigma star, am I going to get for every initial state x the payoff v star of x? So we could say, question, is the discounted present value from playing the strategy, which is also a stationary policy, sigma star, given that I start at any specific initial state x, right? Is this equal to the max or the soup that I can get over all strategies, whether stationary or not, right? We had defined this to be V star of X. Yeah. So clearly sigma star satisfies no improvement with a single deviation, right? So from tomorrow, I'm optimizing and I resolve the optimal trade-off between today and tomorrow by choosing my action judicially. That is my sigma star of X for every X, right? So is this no one deviation also sufficient to clinch optimality, right? And one way to sort of argue this, which would be tedious because it would introduce a lot of notation, because of the various alternative paths that or alternative histories that can obtain, is to say, well, suppose that there is some strategy which can improve. I can see that it can't improve in one step. Suppose it can improve in a certain number of steps, right? Suppose it can improve in the infinite horizon, right? Then, since I'm discounting using a beta which is strictly between 0 and 1, my gains beyond a certain long horizon capital T are very, very little, right? I can make that long horizon long enough such that the gains post that horizon are very little, right? And then I can argue, like we've done earlier in earlier courses, that look, if something can improve, it must improve in one step, right? And so a strategy or a policy like sigma star, which leaves no room for improvement in a single step, must be optimal, right? So here we will use the stationary structure of this Markovian evolution of states and this decision problem to show that this is indeed true, that sigma star is optimal, right? And so here is the theorem. It's theorem 18. It says, there exists a stationary policy sigma star going from states to actions that maximizes the objective function, right? So V sigma star of X for every X is indeed equal to V star of X, yeah, which is the soup across all sigma of V sigma of X. And what is this sigma star? It's given by the following, that for every X, sigma star of X is the maximizer of the right-hand side of Bellman's equation. Okay? So here is the indirect way in which we will show it. And in order to see that, let's use some blank space here. Well, oh yes, yeah, we can use this blank space here. So I will say, consider any stationary policy. Yeah, you could say stationary strategy. Consider any stationary policy sigma, right? So what we mean therefore is that sigma maps only from the current state to actions. All right, and to fix ideas, let me actually fix a time t equals 0. This is not necessary, it could be any time t equals 0, And let's say that the initial x naught is, well, corresponding to the 0 here. Let me not say x naught is equal to x. Let me actually say x naught is equal to a specific state lowercase x naught. Okay. So then, by definition, what is V sigma with current state x naught? It's equal to the expectation under sigma of the discounted present value of rewards given x naught is equal to lowercase x naught, right? So let me open this out. So that's equal to the current reward, R of x naught. So x naught is followed by an action sigma of x naught. Yeah. Plus what happens then in future. So in the next period, the probability that the state makes a transition from x naught to some particular, let's call it x1. Yeah. It moves in a Markovian fashion, but depends on also the action sigma of x naught, right? So this is the probability that the state tomorrow is some specific x1, given that the current state is x naught and that I played sigma of x naught, the action sigma of x naught, right? So this whole thing is the probability, right? So with this probability, I get the expectation, and now this is from tomorrow, the expectation under sigma of the following discounted present value. So let me change, like we've done many times earlier, let me change the notation of the index and call this beta raised to the s, r of xs as, given capital X1 is small x1, yeah, and time s begins at 1 and goes to infinity, right? So this is the expected discounted present value for this specific state, if this specific state x1 occurs, right? And any state at time t equals 1, any state x1 will happen with this generic symbol for probability. So I need to sum across the possibilities of various states, right? Okay, so that's V sigma of x naught, right? And now, like we've done in the past, we change notation back and say let t be s minus 1. So for every s, so s is equal to t plus 1, and s is equal to 0 corresponds to, s is equal to 1 will correspond to t equals 0. Okay, so then I can write this using my index t as r of x naught, this plus it would be good to edit these and fast forward in these places, but what the hell, so let's go with what we have right now. So now the summation will be from t equals 0 to infinity, beta to the t plus 1, r of xt plus 1, at plus 1, given x1 is equal to x1, right? And then I can factor out 1 beta, So since I have one note here, let me use the facility of eraser to do the factoring. Yeah. Hey, that's a different green. Where is my dark green? Okay. Better. Okay, so it's that. And then I draw your attention to this here. Yeah. So this is saying time starts at t equals 0, right? The notation is slightly changed so that at t equals 0, I am given that the state is x1, right? So this should not be confusing. It's saying that, you know, if I say that time t equals 0 happens in period 1, yeah, from the original perspective, then in fact this is my period 0 right now, right? So x1 is equal to lowercase x1 is like my initial state here. And so as we have argued before, we can, you know, borrow the same argument and say that, look, what we have here is the payoff, the discounted present value under the stationary policy sigma. When we start with state x1, so that's v sigma of x1, right? And here I'm multiplying that with a beta. Let me take beta all the way out, factor it out. Yeah. Summation overall of this times and then I have my first reward, the 0th period reward. And so this is v sigma of x naught, right? So look at this relationship. Yeah, it's a functional equation that v sigma solves, right? It's solving this functional equation. V sigma, the function v sigma that maps from states to real numbers is on both sides. It solves this functional equation, right? So what is the, so it must be the fixed point of some map, some Bellman-like map, right? This is not a Bellman map because I'm not doing a maximization exercise on the right-hand side, but it's a map, right? So what's the map for which v sigma is a fixed point? Let me, so for what map from states to states is v sigma a fixed point? So it's this. So let me call that map T sigma. Okay, it is this T sigma from states to states defined by, so I start with some value like function w and I map from that to T sigma of w, okay, and defined by this, that T sigma, let me, now that we are here, let me just use this. So it's 3.2 T sigma w of the state x is equal to r of, if you wish, because we'd written this in terms of x naughts, let me say of x naught is equal to r of x naught sigma of x naught plus beta times summation w of x1 p of x naught x1 sigma of x naught, right? So you can see that if I replace both sides with V sigma for the W here and V sigma for the T sigma W here, that's a fixed point, right? Okay. So there is this lemma which says let sigma be a stationary policy and let T sigma go from the bounded functions on S to the bounded functions on S. S to S is okay here because S is finite, everything is nice and bounded anyway, right? So let T sigma be the map defined here. So here, instead of using my x naught, x1 notation, we are just using x for a state and y for tomorrow's state, instead of x naught for today's and x1 for tomorrow's, right? So let it be defined as follows for all value-like functions w and all states x. All right, yeah. Then T sigma has a unique fixed point, and that fixed point is V sigma. We've already shown that V sigma is a fixed point, okay? It remains to show that this is the unique fixed point. Because this part is very easy, I'm going to mostly skip it by saying that, look, the way to show that T sigma has a unique fixed point is to show that it's a uniform contraction because it satisfies Blackwell's conditions. Okay, it's a uniform contraction with modulus beta. So first, it satisfies monotonicity. Suppose you take two functions v and w such that v is less than or equal to w at each x, right? Then you can see that this second thing here, summation v of y p of xy sigma of x is going to be less than or equal to summation w of y p of xy sigma of x, right? And therefore beta times this is less than or equal to beta times that. So beta times this plus r of x sigma of x is less than or equal to beta times this plus r of x sigma of x, right? So T sigma V of x is less than or equal to T sigma W of x. So T sigma satisfies monotonicity. Yeah. T sigma also satisfies discounting, and you can check that. So here, you know, when you look at your Blackwell's theorem and its proof, we have used real numbers, we've used the symbol A, but here we're using the symbol lowercase a for actions. So I've changed this to a C. Okay, so it's easy to see that T sigma also satisfies discounting. Okay, so it has a unique fixed point, and we've already shown that the fixed point is V sigma. So now we come to this result which is of interest, which says there is a stationary policy sigma star that is optimal, right? So that maximizes the objective function starting with every state x. So that if I employ this stationary policy, I'm always going to get V sigma star of x is the maximum amount that I can get, which is V star of x, right? And what is this sigma star? It's the policy which prescribes the action sigma star of x that maximizes the right-hand side of Bellman's equation for each state x. Okay? So that's the theorem. And here is the proof. So first, notice that, so ignore this for a moment. Notice that we've shown for any stationary policy sigma, something that will therefore hold for the stationary policy sigma star, which is we've shown that V sigma star of X, V sigma star is a fixed point under the map T sigma star, right? So V sigma star of X is equal to R of X sigma star of X plus beta times summation over all states tomorrow. Let's call those states Y. Yeah. V sigma star of Y and the probability of the transition to Y. Right? So we've shown that this is true for any stationary policy sigma. Right? So in particular, sigma star will satisfy, or V sigma star will satisfy this functional equation, right? And so it's going to be a fixed point. So V sigma star is a fixed point of T sigma star defined by T sigma star of X is equal to, T sigma star of some function, let's call it W, yeah, of any function W is equal to this plus beta times expected value of W of Y from tomorrow. Right? So we know this. Right? So in other words, so that is T sigma star of the function V sigma star is just V sigma star. It's a fixed point. Okay? Or if you want, this will always be true. Okay. So now look at the map T sigma star where it's picking up not V sigma star, not the function V sigma star for which it's a fixed point, but the value function V star. Okay, so T sigma star of V star, right? So by definition of T sigma star, that's equal to the current reward R of X sigma star of X plus beta times the expectation under the of the value function V star of Y. All right. But if you stare at this and recall that we defined sigma star of X to be the action that maximized the right hand side of Bellman, right? We can write this as saying that this value is the maximum overall feasible actions of the right hand side of Bellman's, right? But V star satisfies Bellman's equation, so that's just equal to V star of X. In other words, V star of X or V star is a fixed point of T sigma star. But lemma 3 already showed that for any stationary policy sigma, and therefore for sigma star here, T sigma star has a unique fixed point, and that's V sigma star. So V sigma star and V star must coincide. They must be the same function, right? Okay. So then, using this theory, one way to numerically compute the optimal strategy or the optimal policy sigma star is this. we start with the Bellman operator T, okay? So I'm calling, the Bellman map T. So you stare at 3.4, you can see that the value function V star is a fixed point of T, right? If I replace the W and the TW with V star, this equation is satisfied. We showed that V star satisfies Bellman's equation, right? So V star is a fixed point of T, and in fact, it's easy to show that T has a unique fixed point. We've done this in the deterministic case. It's similar here, right? So T has a unique fixed point. So V star is the unique fixed point of this. And the way we showed it is to show that T is actually a uniform contraction. So we can show that here as well, that T, which maps from, so at some point I made an error in notation. Let me correct that. So I'm picking up functions, okay, real valued functions with domain S. So it should be, T sigma is a map from, let's call it, consistent with notation here, BS to BS, the bounded real functions with domain S. Okay, so it picks functions from and carries them into functions. So this uniform contraction is picking up functions with domain S, carrying them to functions with domain S. And from the proof of Banach's theorem, we know that we can start at any W, right? So we can start at any W, go to TW, T2W, etc., to TNW. We know that as n goes to infinity, TNW will converge to the unique fixed point V star, right? So an algorithm will stop when it's assured that TNW is close enough to V star. Right? So we can discuss that later. And once it's stopped, we say, look, that final TNW is close enough to V star, it's practically V star, right? So using that, we can calculate the optimal action sigma star of X for every state X by just picking up a maximizer of the right-hand side of Bellman for every state, okay? So this process is called value iteration. We're iterating on value-like functions until we hit the actual value function. Once we hit the value function or are arbitrarily close to it, we get arbitrarily close to the optimal policy function by using Bellman's equation, right? So we found in step one, we found something which is very close to V star. So once we found something very close to V star, we do this maximization exercise. We take each state X and we choose a maximizer. So we maximize we found our V star virtually. We use that function that we found wherever we've stopped the iteration, and we maximize this with respect to feasible A's. Okay, so state by state we get an optimal action sigma star of x, and that collection or that map sigma star is the optimal strategy. It so happens that it's stationary. It just depends on the current state, right? So I'm wondering, let me backtrack just a little. And say that look, we have sort of seen that it's satisfactory in this setting to restrict ourselves to strategies that are stationary, right? And so for a stationary strategy, not just for a stationary strategy, but for a stationary strategy, sigma, the discounted present value or the expected discounted present value under that sigma starting at state x is given by this, right? And we said that the interpretation of this should be that any strategy sigma, and here a stationary strategy, it induces a probability distribution on the terminal histories, on the infinite histories, right? And so take each infinite history, calculate the discounted present value, multiply by the probability, or if you can't do that because there's a measure theoretic problem here, you do the equivalent limiting operation of Lebesgue integration, right? And that's how you calculate the expected payoff, right? So what you're doing is you're associating a utility, a discounted present value to each path that can occur, and you're weighting these discounted present values by probabilities. So it's an expectation in that sense, right? So now notice that, so again, without having sort of rigorously done expectation in terms of let's say Lebesgue measure or Lebesgue-Stieltjes measure, let's just say that, look, an expectation operator is linear. So if you look at this, what you can do is you can say that this expectation of this sum is the sum of these expectations, right? You can shift the expectation operator inside. Yeah. If you shift it inside, of course, it's not paths that you're now looking at. It's now saying that your expected discounted present value is the following. So now you're looking at saying that you've started life at t equals 0 with x naught equals x, right? Suppose you are looking at some time t. How will you evaluate the payoff that you get from that time t? So this is saying that you will discount the payoff by beta to the t, and you will take an expectation over the payoffs that you will get at time t. Okay, the payoffs that you will get at time t. Right? So how will you do that? You will do that by saying that, look, at time 0 I was at x, So what is the probability with which I will be in different states y at time t? And what is my payoff? What is my instantaneous payoff or reward at time t if I'm in that state y, if xt happens to be a certain state y, and I'm playing my stationary policy sigma, so I'll play the action sigma of y. So my payoff will be r of y sigma of y, right? Yeah. So this expectation says you take each r of y sigma of y, where y is the state that has occurred at time t, right? Yeah, so then that's my reward. I must weight that with the probability that xt, the state at time t, is y, given that x naught is equal to x, right? Yeah. Okay, and I must add over all states y that can occur, right? So notice that I'm doing this at a certain time t, so things are finite, right? Things are finite. So if you want to visualize the decision-making tree, if I cut it off at some time t, I have a finite extensive form. Okay? So it's, of course, things will get gory as we go down and say, hey, I'm going to have to keep doing this for every time t from 0 to infinity, so I'm going to have to take some limit as t goes to infinity. Yes, but ignore that for now, right? We can approximate by replacing this infinity with a long enough time horizon t, such that beta to the capital T is very, very, very negligible, right? So then most of my payoff will have happened by then, right? So for any particular time t, my contribution to discounted present value is beta to the t times expectation, which is this. My rewards at time t, if the state is y, and I play sigma of y, times the probability that the state is y at time t, given that the state is x at time 0. So from here you can recognize that this is something that we can get from the theory of Markov chains, right? So we are using a certain a slightly different notation here to say that Q sigma is this matrix here. It says, there are some states, yeah, a finite set of states, yeah, state 1, state 2, state 3, etc., etc. So let's say this state is x. It corresponds to row x. Yeah. What are the transition probabilities to the states y tomorrow? So what are the p of x dy's? Well, it's actually px y, given that the state today is x and I played the action sigma of x. Okay, so if this is the xth row and this is the yth column, that is the probability entry here. Right? So this is my Q sigma matrix. And then from the earlier Markovs, and so this is the probability that the state will be y tomorrow. Let's say at time t equals 1, if the state is x at time t equals 0. And the Markov chain theory showed us that if we multiply this matrix t times, yeah, we will have here, I don't want to write this out in notation right now, but the xth row and yth column will have this probability, given that I've been playing according to sigma. Right? So the rest of it here, I'm not going to sort of go into in detail. This is, I may have reason to do that later. The point is twofold here. One is that instead of the tough exercise of tracking infinite histories and probability measures induced on the infinite histories, I can convert the exercise of finding expected discounted present value by shifting the expectation operator inside and saying that, look, I'm going to do the payoffs period by period. Yeah, that's one thing. I'm going to do the payoffs period by period. I'm not going to worry about infinity, perhaps, by saying that I'm going to take a large time capital T, and beyond that, even if beta is very close to 1, beta to the capital T is practically nothing. So the rewards are practically nothing, right? The rewards, keep in mind, the rewards cannot grow because everything is bounded here, right? It's not that as beta to the T goes to 0, the rewards can go to infinity. They can't because of boundedness, right? So that's the first point. And the second point is that in terms of computation, what I can use is fast array or matrix methods, using these matrices to tell me what the probabilities are of each state t periods from now if the current state is x. Okay, so we may have reason to see some coding corresponding to this, but I can't promise. So here is an example from originally from Stochastic's 2009 text, and then it sort of appeared in the Quanticon, on the Quanticon website as well. I don't know whether it's still there, with some changed terminology and notation. Here Stochastics talks of kernel Kurtz, which sort of reminds us of a classic novel by Joseph Conrad, and then a classic, so Heart of Darkness is the classic novel where Kurtz is this main character who becomes a demigod in Africa. You could say roughly the setting is one where where today we have the Democratic People's Republic of Congo. And then later, not adapting this, but inspired by this, the classic movie Apocalypse Now on the Vietnam War, where there is a character called Colonel Kurtz, right, who goes rogue. So set all that aside, this is a very simple discrete dynamic programming problem. There's a guy who eats fish, and to begin with has a stock xt of fish, and takes the action of eating fish first. So with xt of fish at time t, he eats ct, and stores the rest, xt minus rt. Okay, so this is very similar to an infinite horizon optimal consumption problem, where there is some consumption, the rest is saved. Here the rest is stored. There is some constraint on the amount that can be stored. Okay, you can't store more than capital M. And then next morning he catches some fish, and that's a random shock. Okay, so if you want to convert this to the language of optimal consumption, you could say that I consume something, I save the rest, and that saving grows because I've lent it and there is some interest. And if that interest is stochastic, for instance, maybe I've saved in equity, right? Then the assets, the value of the asset that I'll have tomorrow corresponds to the stock of fish that I'll have tomorrow afternoon, which is xt plus 1. It's what I saved, what I stored, rt, plus what I caught. So in this example, I caught wt plus 1 fish, and wt plus 1 is an IID sequence distributed according to phi, yeah, on this set. So I can catch any number of fish that starts from 0, goes up all the way to some maximum number, capital B. I have Kurtz has a per period CRRA utility function. U of c equals c raised to the beta. It's unfortunate that this is beta. It's beta in Stahersky's book because we've been using beta for discount factors. So now we'll use rho for a discount factor. And we saw that optimal policy can be restricted to stationary strategies, right? So say he uses a policy function sigma that maps from current stock into how much to consume, alternatively into how much to save, right? So since the current stock xt cannot be more than b plus m, right? So m is the maximum that could have been stored, and b is the maximum that could have been caught, right? So xt must be less than or equal to b plus m. Effectively, we can say that our state space is the following numbers, starting with 0, going up all the way to b plus m. That's what any xt will occupy, one of these, right? And a stationary policy will go from this state space 0 to b plus m to here how many fish to store, could be how many to eat, whatever, how many to store, 0 to m to store. Satisfying feasibility, that is the number that you store, sigma of x, must be less than or equal to the number that you have. And let capital sigma be the set of all these stationary policies. Then v star of x, the value function we showed, will be the max across all these stationary policies of this discounted present value, right? So utility from consumption is from consumption c or ct in period t is ct raised to the beta. So that's xt minus what I store, that's my consumption raised to the beta, right? Discounted by beta to the t, okay? And I maximize this subject to the evolution of the state variable, the fish. And this is how the state variable will evolve if I choose my stationary policy of storage to be sigma. Right, so tomorrow the fish tomorrow xt plus 1 will be, if it's xt today, it will be what is stored, sigma of xt plus what is caught, wt plus 1, right? Yeah, with wt IID and x not given to be x, right? So you would have seen such sort of difference equations, certainly when you were doing deterministic things, but also just stochastic difference equations, right? They're just time series, okay? And so the rest of it is this is a discrete problem. How do I solve it? So one way would be to code this and use value iteration, and I will be doing that, but that will come a little while later, because we'll start with picking up some of the language of Python.